At its core, the study of force fields is a study of how energy is transferred to an object as it moves through space, a concept known as work. The sources distinguish between two types of environments: conservative fields, where the journey specifics do not matter, and non-conservative fields, where the path taken dictates everything. The nature of conservative fields. In a conservative field, such as a radial field where forces point directly away from a center, the total work done depends only on the starting and ending points. This can be visualized as a topographic map of a hill. On this hill, height represents potential energy. If you travel between 2 points at the same elevation, the net energy transferred is zero, regardless of whether you took a direct straight line or a long, winding path. A unique characteristic of these fields is the round-trip rule. If you move in a complete circle and return to your starting point, your work accumulation resets to zero because you have returned to the same elevation or potential level. This is why a conservative field is often compared to a GPS. It only cares about your specific coordinates, not the route you use to reach them. The nature of non-conservative fields. Non-conservative fields, such as the vortex field, behave very differently. In these systems, the forces often swirl around an origin. Because the force is not derived from a single height-based potential, the energy you gain or lose is path-dependent. Every extra inch of travel can lead to more energy being transferred or leaked into the environment. Unlike the GPS-like nature of conservative forces, non-conservative forces act like an odometer. They record every turn of the wheel and every bit of resistance encountered. If you move an object in a circle within a vortex field, the work does not reset to zero when you return to the start. Instead, it keeps growing as the field continuously pushes the object along the curve. Why the path matters. The derivation sheet illustrates these differences by comparing how a particle behaves on circular versus straight paths. In a vortex field, a circular path often accumulates more work because the swirling force vectors are perfectly aligned to push the particle forward for the entire trip. A straight path through the same field is less efficient because the force often pushes sideways or at awkward angles. In a radial conservative field, a circular path results in zero work because the force always pushes outward, perfectly perpendicular to the direction of motion. It never helps or hinders the particle. On a straight path, the particle might move inward against the force, creating an energy debt, but as it moves back outward toward its destination, the field pays back that energy, resulting in a net total of zero. Ultimately, these concepts help scientists and engineers determine whether energy is being stored as potential, like a compressed spring, or dissipated, like heat from friction, during a journey through a force field.